Okay. Now we're going to talk about the mechanics of mixtures. So we always have to start, when we talk about continuum mechanics, we always have to draw a potato. Same as before, we have a reference configuration, and we have a current configuration. We'll call it this guy B0 and this guy B. We have an inertial reference frame, and I'm going to start by drawing the current configuration. So actually, I'll start in reference configuration. So here, we're going to assume that we have a mixture of two species. This holds, what I'm presenting holds for n species, right? But just to make things simple and clear, we're going to talk about two species or components of the mixture. And in our case, because we're ultimately trying to derive equations of Portal mechanics, right? We'll just specialize that to a solid and a fluid. But again, what I'm going to present would hold for multiple fluids, multi-phase flow, things like that. Okay? So each of these guys in the reference configuration has its own big X position vector that now we'll put a superscript on for F for the fluid and S for the solid. And we're going to formulate these equations, or as you'll see later, we're going to have a constraint on these equations in the in the current configuration. And that constraint is only valid in the current configuration. And so what we're going to, when we derive the equation, I'm going to say we're going to assume, but it's not a restrictive assumption, it's just an assumption. We're going to derive the equations under this assumption. Okay? That in the in the current configuration, the two species that we're tracking are in the same exact point. Okay? So they share an identical position vector, little x, and that little x, we don't need a superscript on it because it's the same for both of them. It's just the current position. Okay? And so then, but how they got there will be two independent motions, right? So this is like the symbol chi of the fluid. Chi of the solid. Those are two separate things, right? So what we'll write is that the current position vector, little x, is equal to chi alpha, which is a function of its original position vector and time, for alpha equals S and F. Okay, so there'll be several equations that I write in the future that hold for both S and F, and in those cases, I'll just use the symbol alpha. And that's why I say it really, my drawing is specialized to two species, but it would get busy if I had 100 species on that drawing, right? but anything that I write in the future that has a component, an alpha is basically meant to be the alpha species, and that holds whether you have 2 or 4 or 100.
Why did you assume that it would converge to 1 point?
Well, you'll see in a second, because ultimately we're going to have a constraint at this point that the volume fraction of the species add to 1, right? So, and this, you might be thinking like that's an assumption to say that two things in the reference configuration end up in the current configuration. But think about it the other way. Think about the inverse mapping. So you say in the current configuration, there is solid and fluid. And we're going to say that the solid and fluid that's in the current configuration now came from two different places in the reference configuration. At least in general, they could have, right? So it's, that mapping chi is, and this is all in all of continuum mechanics, that is, it's smooth, it's assumed to be smooth and one-to-one so that it's invertible, right? So I can go the other way, right? I can ultimately I'm going to write the equations, well, I'm going to formulate the equations in the current configuration because the volume fraction constraint holds in the current configuration, right? Okay. Let me just okay, so just like before, we have now the deformation gradient of, again, I'm going to use the alpha subscript. So we have two deformation gradients, right? One for each species. That is the partial of chi alpha, partial big X alpha, right? So you see that that's equal to partial X, partial big X alpha, right, where these are vectors. So that there's no difference there than before, it's just now we have a superscript alpha because there's one for each species, right? So a lot of what you're going to see we've already covered, right? Just now we're going to put superscripts on. All right? So similarly as to before, we know that, from vector calculus, basically the Jacobian of the deformation gradient can map volumes from the reference and current configurations, right? And so we have the same thing here. It's just in the current configuration, d little v, that maps to j alpha dv0 alpha, where j alpha is equal to the determinant of f alpha. So, just like before, we have a statement of conservation of mass. The integral over B0, rho 0 of x alpha dv0 alpha is equal to the integral in the current configuration all right, so just kind of following our conventions from before, this is written in the reference configuration, so I have the body in the reference configuration and dv0 alpha, right, because each component has its own dv0, right? But in the current configuration, they all occupy the same volume, right? So this is just saying that the density of each species, by the way, this density is really, it's the volume of the alpha species divided by the total volume, right? So it's the volume of the alpha species divided by the total volume. I'm sorry. It's the mass of the alpha species, right? So we'll say that rho alpha is the mass of the alpha species divided by dV, right? The total volume. Or maybe just to be consistent, I'll just put the D's on there. Right? But it doesn't really matter. Okay. And then if I, any time that there's a subscript 0, so I'll just write it. Subscript 0 indicates evaluation in the reference configuration. Same idea as before, right? Okay. So now we can take this definition, substitute it there, right? Another way of saying this in continuum mechanics is a pullback operation, right? We're going to pull back the current configuration to the reference configuration through the Jacobian determinant, right? So if we do that, then we have integral over B0, rho alpha 0. Now I'm gonna try to, anytime I write a field variable, I'll try to initially write, what it's the function of, but after that I'm gonna drop them just so the equations get more condensed, right? So rho 0 is only a function of its initial position vector. It's not a function of time because it's a reference position, right? So we have that. dv0 alpha. This is equal to the integral of rho alpha j alpha dv0, and that equation must hold for any arbitrary volume dv0, so that leads to j alpha equal to rho 0 alpha over rho alpha. Right? We had that equation before. That's a statement of conservation of mass. The only difference now is that we have an alpha superscript. Right? Is that. So basically, we have a statement of the conservation of mass for each species. Okay? So now introduce the definition that the rho alpha is equal to phi alpha. Phi is a function of the current position vector x and time times rho bar alpha. Okay, so rho bar alpha is then equal to the mass of the alpha species divided by the volume of the alpha species, right? So this is more like the true density, or sometimes we call it the local density, because that density up there is the density of the alpha component divided by the total volume, right? This density is more like what you'd expect, right? The density of the alpha component divided by the mass of the alpha component divided by the volume of the alpha component, right? And so if we take the local density, we multiply it by porosity, or really in this case, it's not a porosity, but it's a volume fraction, right? Well, because again, if everything I wrote will hold for, say, multiphase flow. If it's multiphase flow, it's not a porosity, right? Later we'll see that in this problem, the fluid volume fraction turns out to be the porosity, right? But for now, let's just leave it as alpha, because you wouldn't call it a porosity if it was a volume fraction of a multi-component fluid, right? Okay. And also, we have a volume fraction constraint that says that this total sum of all volume fractions must equal to 1. So this is called the volume fraction constraint. Okay, so for simplicity, we're basically saying that this is a fully saturated mixture, right? There's no partial saturation or air or gas, right? But basically, whatever's not solid is fluid, okay? However, you can extend, again, what we're doing here to partial saturations by just adding a third component, say air, right? And then you can extend it. So basically, this is just saying the sum of the alpha components equal to 1, okay? For our problem that we're looking at right now, for alpha equals a solid and a fluid, then we can just write that as phi of the solid plus phi of the fluid equal to 1. Right. So if we plug this relationship for the density, the volume fraction times the local density into the statement of conservation of mass up there, then we have, a same statement of conservation of mass, but just in terms of the local densities, right? So we'll have J alpha is equal to phi 0 alpha rho bar 0 alpha over phi alpha rho bar alpha.
Professor?
Yep.
The phi 0 doesn't depend on time, right?
No, it doesn't. No. I mean, yeah, it's just phi what it was in the reference configuration where you started. Yeah, so the things in the numerator are constants. All right. So